And hi everyone, welcome to the future of Urban AI season 3. My name is Hubert, I'm the founder of Urban AI and I will be the host today. For the third episode of season 3, we have the great pleasure of welcoming today Brandon Barbello, COO of Archetype AI. And Brandon will actually tell us more in this episode about Archetype AI, what they are doing, and also the concept of physical AI. Hi, Brandon. And to tell you more about the future of Urban AI webinar series, it's an ongoing collaboration with Cornell Tech, between Cornell Tech and Urban AI from now, actually the last 2 years. Every year, we are exploring the future of urban artificial intelligence with worldwide experts from really all around the world with diverse expertise. And for the third season, again, we are embarking with amazing panelists, experts, like Brandon. Last week, we discussed the use of AI for sustainable cities with Josephine Hinz, Ruth Nelson, Tanya Fu. And next week, we will talk about AI on the street with Alex Taylor. All previous episodes are already available on Urban AI YouTube channel. So previous episodes from season 1, season 2, and actually also early season 3. The report of the season 2 which condense the main insights from last year exploration, is also already available on Urban AI and Cornell Tech platform, and we will share the link in the chat. And lastly, we are starting a new collaboration based actually on this project with Cornell Tech, who is launching a mapping platform called Intelligence for Climate Adaptation. We will also share the link in comments, but basically the goal of this project is to explore the use of urban artificial intelligence for cities climate adaptation. But today we will talk about physical AI with Brandon from Archetype AI. As usual, we will have 20 minutes of presentation, between 20 and 25 minutes of presentation from our speaker, Brandon, and then we'll have 20-minute Q&A session with all of you. So if you have any remarks, any questions, feel free to use the chat and we will ask your question. Brandon, the floor is all yours.
Wonderful. Thank you, everyone. All right, I've got my slides back up and I'll take it away. Great. Yes, so at Archetype, we are working on AI for the physical world. And today I'll focus less on the company and the product and more about how we think about this and what direction we think the world needs to move in to get AI to a place where it can help us to solve really difficult real life problems. And so how we see the world naturally is that it is full of data. But much of the work in AI today is focused on data from the web. We have things like large language models focused on text. There's increasing work on images and for video, but there's also all this other data that doesn't quite get the same amount of attention. There's of course video, but there's also things like radar and LiDAR, there's audio, and there are all of these machine sensors, things like temperature, vibration, pressure, telematics from a wide range of machines, from vehicles. And we think for AI to help us to solve physical world problems, AI has to understand the physical world natively. It has to be able to learn directly from these sensor signals, things about physics, things about behavior patterns, things about physical systems. And so the direction that we have been working in is how do we expand the architecture of these large foundation models to be able to understand all these additional kinds of data? To step back a bit, of course, a foundation model refers to a large AI model that is able to do many, many tasks. And so it's a more general purpose approach to an AI model. And you may have heard of a multimodal model, those models, for example, like what ChatGPT uses, where you can use voice and images in addition to text. And so you can think of what we're doing as trying to be massively multimodal to incorporate this much larger universe of physical data. So how we see the path from here is that there's a need for a unified model that's able to encode the entire world from sensor data. And in doing so, That's how AI comes to understand the world and then comes to help us be able to solve these real world problems. We think the unified model approach is important because all these different kinds of sensor data, they each measure reality in different ways. And some of those ways, like video, are analogous to our human senses, but they're at a scale that we can't keep up with. There are simply so many cameras running 24/7. But these signals are also things like radar that have a very non-human kind of perception. And each of these sensors really, in effect, it measures a different way, a different facet of reality. And we think this approach is required to put them all together into one complete picture, including a picture that goes beyond human perception to enable us to think at a bigger scale to solve uh, urban management problems, climate design problems, business problems, where you have these large, spatially large and complex systems. Now, this unified model approach is in contrast with how things are done today, because today there's of course things like computer vision, and there's different statistical approaches, for example, to analyze one's time series data. But whether you have cameras looking for public safety risks, or you're monitoring traffic, or you're looking for equipment failures, current techniques allow you to only build narrow models, pretty much one model per sensor and per use case. And doing so requires you to train that model with a lot of data and requires you to have a lot of expertise to make that model well. And so we here see a bottleneck insofar as IoT and industrial sensing has made it possible to collect all of this physical world data, but it's still beyond the reach of cities and of businesses to extract all the value they had in mind when they began to deploy these sensors. And so how we see our foundation model approach is that not only can we integrate all these sensors into one big picture, but we can pre-build a model approaching general purpose use over time for the physical world. And this pre-existing model can be used by any developer that has access to sensor data. And their data with this model, even if that developer has no expertise in AI or even no expertise in sensor signal processing, they should be able to take their data with a model like this and rapidly solve some physical world problem. So we're trying to remove that bottleneck on what developers can do with their sensor data with this pre-built model that democratizes who can build things with sensor data and dramatically widens the scope of what's possible for them to build. Now, when it comes to solving AI for the physical world, we see three core challenges to be solved, and I'll touch on them each in the course of this presentation. The first is, as I've been talking about, how do you bring the physical world into these models to make it understandable through these additional kinds of data? That's number one. Number two is, if you do that, how do you make that model usable to someone with real physical problems? Because that person probably isn't a computer scientist. They probably aren't behind a desk with a bunch of screens. And so how do you make that interaction physical? And then third, how do you make the AI physical insofar as you bring it physically into the world in some kind of a manifestation where the AI comes to the data as opposed to the data coming to the AI running fully in the cloud? And so these three challenges of the model building, the interaction, and the deployment, we think are key to unlocking the potential here. But the model itself, our approach fundamentally is to project this sensor data into one mathematical embedding space with natural language. And this serves in a very, very simplified sense to make that sensor data computable with semantic meaning, with this kind of textual knowledge that we as humans use to describe and to understand the physical world. The result of that from the model's point of view is that the operator or the developer can then use natural language, similar to prompt engineering for large language models. They can use natural language to steer the model. The model can thus do some task with the sensor data, and then the model can communicate back. It could have a conversation with you. It could output a visual. It could output some kind of a structured text in response to your query about the sensor data. And so it's this interaction through natural language and multimodal prompting that we think is really key to solving that second problem of how do you make this usable to as many people as possible to apply to their physical, right now, real-time problems. And so fundamentally, this model, it's this kind of a translator from signal to meaning. My signal might be more video that I could possibly watch, or it could be a thing like radar that I can't perceive. But through this model, I can get meaning I can use to make better decisions about my city, about my business, for solving problems. So let me show a few quick demo examples, and I'll actually have the audio off for these. So here's a first and simple example of, on the left, we have a signal, in this case, a radar signal. On the right, we have meaning, this running transcription of what the person's doing. And now, historically, to build even a simple thing like this, you would have to be an expert in radar and build a signal processing pipeline. But now, with models like we are building, you can take an API, hook up a sensor feed like this, give it a natural language prompt like, tell me what the person's doing, and this kind of a system simply works. And thus is a tool to understand these continuous streams of data. A key part of this interaction problem and this model problem as well is that the physical world is constantly changing. And so for some applications, maybe a chatbot is best, but for most others, you want to be able to continuously be monitoring something. And so our interaction metaphor with natural language, furthermore, is a little bit different. It's about these continuous tasks, this continuous steering through what we call a lens, which is a bit analogous to like an agent. And so here's an example of this applied. So in this demo now, we have a motion sensor, and we're going to put it in, say, a package. Maybe it's a high-value pharmaceutical that's very shock sensitive. And here you see us activate this lens for transit status. It's going to monitor the transit status. So now the AI takes on this continuous job of reporting back in real time when the package is still, when the package is moving. But what's really great about this natural language interaction is that you can go back in on the fly and just retype to refocus what that lens is doing. So now it's going to shift gears and do package mishandling. And so you'll see the model reporting back if the package is shaken, handle gently if the package is dropped. But this is so powerful because he didn't have to build a new model. He didn't have to make a new data set and do a bunch of labeling. Because he had this pre-built general purpose model, he was able to simply on the fly build a new use case, build an effect, a new application for his sensor data. And that's the kind of interactivity that we're excited about for how a frontline person working in the physical world can collaborate with an AI to solve emergent questions or solve emergent problems through this continuous interaction. Now, very key to our approach as well is that the model isn't only multimodal in, it's also multimodal out, insofar as this is still a generative model that's able to create various kinds of visualizations and such for communicating things about data back to a person. And so as outputs for the model, we can do things like generate a bounding box semantically to annotate some visual data. Or in an example like along the bottom here, we can take a signal like a dash cam feed, and maybe that feed is looking for traffic hazards, for car crashes, for construction zones, for emergency vehicles. You can take a signal like that and a second signal like what's the GPS location. And then you can put those two together as an output from the model as a pin about where you see some kind of a hazard. Further, here are examples of summarizing that. So now I can take all those pins and build a heat map of where I see damage to roads, damage to public infrastructure. Where should a city prioritize where they put their maintenance dollars? You can also output various kinds of charts. And so if I need to consume things as a chart for my business, what's the best visual to show that data? And so this was some work we did, a demo with a bit of a 5G traffic camera sort of thing up in Bellevue. And we were able to both do real-time monitoring of what was coming through the intersection, but also ask summarization questions like you see here, how many cars went east? And the lens that we had built with the model was able to understand, for example, which way is east, that east has 2 lanes, and the model made this interesting sort of an output here where it actually plotted the car count differently for the 2 lanes because they each correspond to a different turning behavior. But so the moral of the story here is these models should be able to communicate these complex data responses back to people in the right format beyond text that a person might need to fully understand and use that information to make some decision. Let's show one more demo related to this that puts a few of these things together and begins to touch on this idea of AI at the edge. So in this demo, this is for a conference in Seattle a few months back. We used a drone that was connected on a private network to a local computing system. And what we did with the drone was we had it hover, and as the attendees for the conference were walking to the conference center, we collected this visual data on their pedestrian traffic. And as a result, during that demo, we were able to show live, asking a mix of real-time questions plus summarization questions. You also see here too in the interface, the bridge is green, the tracks are purple, the roof is blue. We're also able beyond text to spatially prompt and focus different kinds of questions and different kinds of thinking by the model on different physical spaces. So you've seen us ask so far, how many people are on the bridge right now? And then what was the peak traffic? And throughout this, we ask a series of questions about the different zones, but very importantly, also going a bit deeper about if the model can reason more deeply. So for example, why is it a risk to be on the tracks? Because the tracks could mean you could be hit. But also a question like, how many chickens crossed? And the model staying grounded on the factual data, because part of the problems with large language models are hallucinations. But when we can ground a model on real physical data, you can constrain the space of factual answers to help the model itself remain factual. And so quite a few concepts there in terms of, again, multimodal interaction, real-time interaction, summarization, and this ability to ask this range of questions that go beyond computer vision to have more of a semantic understanding of the spaces and behaviors that you are asking about. Here too, by the way, we also happen to output a different kind of plot that shows the pedestrian traffic. Another interesting example of this relevant to the audience today is one of our first developer partners has launched the first app based on the work that we have been doing. And so what this app does, and has now about 5,000 users, is it turns your phone into a dash cam. And then as you're driving around a city, it takes that mapping technique I mentioned a moment ago. And as your phone, as your car sees crashes, sees emergency vehicles, sees construction zones, it automatically plots that on a shared navigational map. And so it's a bit like an automated version of Waze or like Google Maps, but in effect, it lets you crowdsource this real-time information about what's going on within a city to make everyone else more aware of what's happening around them. And you could imagine in more of a smart city context, how you might use the city's vehicles, the buses for example, bus-mounted sensors in combination with a model like this to give that city more real-time awareness of what's happening, all the current conditions, and where resources might need to be allocated. I'll close in the last few minutes and open up for questions with a bit more discussion of of the future directions that we have been exploring. So first up, this is the architecture that we had used for that traffic camera demo and for that drone demo. So much when people think about how compute happens, they think about it's either in the cloud or it's fully at the edge. If it's in the cloud, it's often because someone remote has to deal with a lot of data and a lot of compute is required. If it's at the edge, maybe there's a need for high latency or a need for strict privacy or for confidentiality. But if you think about the physical world, you need to address both. This massive aggregate amount of data, like across an entire city, but also say building or intersection or public space specific queries. And so there's work that we're doing through the pilots that we have started that explore these hybridized approaches where maybe you might locally do some computation, and there you might restrict the removal of data, or you might simplify data, or you might offer some kind of a high latency service. But then you might take the insights that are a bit less privacy sensitive and send those to the cloud, where someone can then query across many locations and do more of an aggregate analysis. And so this question of AI applied at all the right levels to understand different kinds of needs is really key for the future of the deployment question. Next, on the model side, it's one thing to pre-build a model that learns a lot about the world. But if we use today's approaches, we're going to have to build different front ends, if you would, different encoders for every single kind of sensor. There are simply too many sensors in the world, practically, for that to be done. Second, you would have to label a critical mass of data from all these different sensors, also very challenging, going to take a very long time. And so we're exploring some newer approaches that seek to enable the model to learn from observation. If you think about how people learn, we as babies learned about gravity by seeing things fall. We maybe couldn't write the equation for gravity, but we could learn that physical concept. And so in a similar way, can AI learn like we do from observing? And can this accelerate how quickly we could build a general purpose model for the physical world? Because it could learn directly from the sensor data and remove these bottlenecks on having to process different kinds of data differently, or to have humans label and describe to the AI what all the data is. And so this is a paper we've recently submitted to a conference, and at TED.ai in a couple of weeks, we will share some more of these results to date. Lastly, to close, if folks are interested to learn more beyond this presentation, we have quite a few blogs on our website thinking through different questions about how you interact with AI in the physical world, or how we would actually solve these physical deployment questions. Finishing with the company itself, all this work is very exciting, but for it to matter, it has to be applied. It has to show real results. And so there are pilots we are running with a variety of customers across verticals that are helping us to validate that these approaches, that versions of this model hold up in the physical world and succeed at helping them to operate better. And furthermore, that this model approach is able to generalize across solving that wide range of tasks using that wide range of different kinds of data that describes reality. So thank you all for your time today, and I will close there for questions.
Thanks a lot, Brandon, for this fascinating presentation. Actually, also presentation opening new perspectives, maybe from what we usually see in terms of the use of AI for smart city application or city application. So thanks for sharing this insight about your fascinating journey to create physical AI. We actually have already several questions. And by the way, if you have questions, reaction, feel free to use the chat right now, and we will ask them to Brandon. We actually have some first questions from Anthony. Anthony, do you want to use your privilege of host to ask directly your questions?
Yeah, I just was wondering if you could comment, Brendan. Thank you for fascinating talk. Sort of how your understanding of like how the model is either trained or prompted to understand some of the like geospatial concepts that it seems like it's using. Like for instance, the demo where you said, how many cars are pointing east. Um, like, is that something that's learned or is it fed in as context? Like, how is it understanding that as far as you understand?
Uh, yeah, sure. So, uh, this model's approach internally is to, in effect, um, be a bit of a Rosetta Stone across all these different kinds of data. And that's difficult to get to work. But when it works, it makes it a lot easier to solve these problems because before you might only have had the camera. And somehow from that one camera view, you have to understand, like you're saying, these really complex uh, uh, geospatial questions. But when you confuse the data together, you can give it a wide range of information like that from a compass, or you can give it a map, or you can simply with natural language take a second and be like, that way's east. And so it lowers how difficult it is to put these concepts together to have some kind of data help it reason over some other kind of data. Yeah.
I might also have actually a question for you, Brandon, and then I will share all questions from the chat. Just to be sure to have well understood, for example, when you have your Newton, your foundation model that is understanding or identifying an object, an urban object. So here, are you using computer vision or are you using something else? What are you using in this case?
Yeah, so for anything involving do I see an object, that is using the vision component, right? And how we think about that is that we are gradually bit by bit building a model that's learning more and more about the physical world. And so we, in advance of a customer, for example, is going to use it, we've taught it a lot of things. So it recognizes people and cars, and maybe 1,000 additional things. Maybe though, that user has a need to recognize something that it hasn't seen before. And so they can then take a little bit, an incremental amount of data, and we can fine tune the model to teach it that new specific thing for the city. And so, yes, it's computer vision, but it's computer vision that you can fine tune to add concepts. And it's computer vision that's hooked up to the rest of this model such that you can then talk to your camera metaphorically to ask it questions about what it sees or what it has seen. And we find too that when folks begin to engage with us on the computer vision level, they very quickly have some other data that they want to combine with the camera feed. And that then quickly moves beyond computer vision when you're in this multimodal sensor fusion space that allows you to ask these deeper questions.
Okay, thank you. We have also other questions from Tanya, actually, who were presenting last week for our webinar on AI for Sustainable Cities. And Tanya is asking if you can elaborate a bit more on how embedding AI in the real world reduces hallucination. And a related question, from your personal experience, do you think people tend to trust a physically embedded AI more or less?
Sure. So, this work is very early. This is quite early days for these kinds of architectures applied to this kind of data. But how I think about the hallucinations question is that, overall, language or not, these models do a better job of answering questions factually if you're asking about data or information that the model has access to. And so insofar as we can give the model very concrete and objective data, and the model's job is to give the most likely response, you are making it easier for that model to stay grounded on that factual data. Now, if I were to go to that drone demo and ask, what should I have for breakfast? maybe then it's going to riff and deviate from what the thing at hand is. But that's where you can use this notion of a lens or this notion of an agent to constrain what the task is. Because you shouldn't deploy this model as an open-ended model. You should deploy it as a series of these lenses that are focused on solving specific tasks and provide you some structured output to help you do action with that task. And so to summarize, giving the model objective factual data through sentences with which to answer the question, and then giving the model more structure than maybe a language model for how you want it to reason and to output, that we think is helpful to constrain this hallucination space. But of course, there's more research work for us to do.
Okay, so two possibilities. One, when you are targeting data and here less hallucination with your model, and when you are asking to make reasoning, here you have more risk of hallucinating. And can you constrain your model maybe for a city like to only target information and not reasoning?
Right, and in fact, kind of a common thing for us with our developer customers is that our model is going to output something, and it's going to go through an API into some other application, and they don't want like a big open-ended output or a big bunch of text. They want something that's a bit more like a JSON file where they can predefine, I just want the count of people. I just want to know what direction a thing is headed in. And so that's the kind of a structured kind of an output that you would configure with the lens to constrain and focus what kind of a response the model is going to give you, because then you have a consistent response format about the thing that you care about that you can then readily pass off to whatever application is ready to receive that structured output as a new structured input.
Thanks, Brandon. And we have a question from Brenda, who is asking, can you further discuss navigating from private to public and the matter of consent for captured images and storage, people, etc., etc.? Because indeed, your model is very powerful, so they might have maybe also risk about privacy concerns. Yeah.
Thank you for asking, and this actually connects to like a part of the previous question I had forgotten to answer, so I'm glad. So we think of our model as a tool and as really a developer platform, so that those that have this sensor data are empowered with more options to use that data to solve their problems. And so one piece of this is that if you are a city, this empowers you as the city to build your own solution, or have someone that you trust and are happy to work with to build a solution for you, as opposed to buying a black box from some faraway company. And as you do so, you have the ability afforded through this model to take our model, to fork it, and we can't see it and we can't use it, and fine tune it with your proprietary data. So you maintain ownership of your data. You, in effect, create a private exclusive model for the thing that you care about. And then that model, you can run it where you want to run it. You can run it on your sovereign cloud. You can run it on your local infrastructure on-prem in some edge device. And so we want to give developers and people solving problems more options about how they build a model, empower them to build it themselves, give them more options for where it's going to run in a way that they are comfortable with. And furthermore, too, by the way, this ability to work with different kinds of sensor signals, it also means you have alternatives to just cameras. You could, for example, use radars to be a bit more privacy preserving within a physical space. You could use maybe a different kind of time series signal. And so we want to bring more options and tools, and then it's up to the developer or the city to build the right solution in combination with the private space, with the public space, that's going to conform to the norms and the expectations and the regulations wherever they're going to be deploying some physical AI system.
Thanks, Brandon. And we actually have a question from Jane echoing your answer, who is asking, have you already engaged the public sector to pilot this AI?
We have some ongoing conversations and explorations, but they haven't yet reached the deployment stage. But we are quite excited about it because we think these are the most important problems to solve. It isn't always easy for a city and a startup to work together, but there are increasingly a number of cities trying to find good ways to collaborate, and so we're eager to engage and to meet with more and more of those cities to unlock the potential benefits of this model as soon as possible.
And we have maybe the final question from Spencer, who is asking, Fei-Fei-Li's World Labs seems to be trying to build a similar model, but they haven't released much in public information. Do you know how your approaches differ? And do you have any sense of a timeline for when these models will be more broadly applicable?
Yeah, I mean, her work is very, very cool. I mean, I don't want to speak for her. I understand from what they've shared recently in podcasts and in presentations and things that they might be working toward a similar goal, but they have a different approach, which, as I understand, is that they're gonna start with learning from simulations first and try to build kind of a generative way to create a virtual world. And maybe that's applicable first to gaming or to media creation or to augmented reality. As I understand it, they want to do that kind of a thing first before coming to the physical world, though I think they have ambitions to do so at some point. I think our approach is more about starting with the sensor data and starting with the physical world. We aren't generating, any kind of a virtual world sort of a thing. But in any case, I think we're at this wonderful moment in the field where a lot of people are excited to try a lot of different approaches. And I think the more approaches, the more people try, the faster someone's going to find the right way to solve these problems and to make it possible, really for anyone to be empowered with these tools. Yeah, I'm rooting for her, and I'm excited to see where the field is. For our part, in terms of timeline, we are still at a bit of an early stage. It is a many-year journey to build the full vision we have for a general physical purpose model. But we have a beginning. We are learning rapidly through the pilots. Next year, we might release some early versions of more self-serve tools so that more people independent of us can begin to experiment and to try things. But between now and then, I'd love to engage with anyone that is interested in collaborating on a pilot to explore and to help us test and validate that we are on the right track.
Thanks, Brandon. And I have actually maybe a last question because in the video you showed to us, it looks like the interaction between the model and people is actually quite easy, like frictionless. When we are mentioning generative AI, we sometimes have in mind, prompt engineering or this kind of skills, or that have been said to be like new skills. So it looks like you are moving beyond prompt engineering, like it's becoming in a way useless with the interaction you are proposing here.
Yeah, I mean, I think to be humble, I mean, I think I wouldn't say that this kind of natural language interaction, it isn't like not prompt engineering, but you're right that it's quite different from how people think of a prompt today and how people think of interacting with an AI, which a lot of people default to. It must be a chatbot. It must be some kind of, I ask a question, I get an answer, back and forth and back and forth. Yeah, I mean, I think the evolution we're moving toward is that it's more of a real-time thing, more of a continuous thing, more about steering as opposed to a call and response. And as you saw previewed in the drone demo, where part of this spatial information was used for the lens, also going beyond text and going beyond speech. What if I could point to something, for example, and ask a question about it? Or what if just a thing I did. What if you walk into a room and that is a prompt to trigger something? And so thinking more broadly beyond text, thinking about more of a real-time and continuous system, we think that is the right way forward for how prompting and the like evolve for the physical world.
Amazing. Thanks, Brandon. I'm smiling about Anthony comments, and indeed, maybe we are creating like magicians.
Yes.
I mean, I think in so many ways, this is the missing piece in a lot of visions of ubiquitous computing that go back 20 or 30 years. So it's really exciting to see, what I think a lot of people have been skeptical of, around the chatbots having such a pragmatic application in the real world.
Thanks.
Well,
yeah, it's really exciting to follow. Thank you for sharing this.
Thanks, everyone.
Thanks a lot, Brendan, for your presentation, for taking the time to answer all those questions. Definitely let us know about future urban AI applications you might have. It will definitely interest us. Thanks to all of you for your participation. Next webinar will be next week, actually, same time, with Alex Taylor, and we will discuss this time about AI, civic engagement, and public trust. So it's related to one of the questions we had earlier today. The recording of this video will be available in the coming days in the Urban AI YouTube channel. And in the meantime, I wish you all a very good week and take care. Bye.
Thanks, everyone. Bye.